Okay, well, it looks like that's all we're going to get. So um, I just want to, okay, so tonight we're going to have Steve, Dr. Steve Borstelman leading us through, beginning to lead us through this, the chapter on um, uh, unsupervised learning techniques. But before we do that, I'll try to finish up what we did for finish up the chapter 8 part from last time. So I'll just take 15 or at most 20 minutes to do this. That's a hard limit, and then Steve will stop me if I get too enthusiastic and keep going. I'll try to limit it to 15 or 20 at the most, and then we'll go to Steve's presentation. First, I'd like to remind everyone that this weekend there will be no classes. It's the Labor Day weekend in the United States, so we tend to want to have a weekend off. So we won't have another class until next Wednesday. So, any questions? Any questions before I start chapter 8? Any questions left over from chapter 8? Okay. Let's see. I will share this. Everybody see the dimensionality reduction notebook that I've been sharing?
Yes.
Okay, great. So let's back up through there. The first thing I wanted to do was redo or go over this time complexity section, because I think there was some, there are some, it's kind of like an error in the code. He wants to compare regular Pca versus randomized Pca, and the thing that bothered me was the two graphs that were given in the code I think they were both in the book and in the notebook, didn't show that randomized Pca was any faster than regular Pca. That the two lines were very close to each other, so it really didn't make the point that I think he wanted to make. So I looked into the code and found that if you change the dimensions a little bit, he had like a n components was equal to 5, I think. And that's a very small problem. That's not a problem where you would expect, where you'd be motivated to go to a randomized Pca to get speed. So I increased the number of components and to 20. And let's see. Yeah, and I also increased the number of components in the problem. In other words, the full problem we're trying to solve has different numbers of samples, going up to 100,000. But the number of features I think he had the number of features was really small. It might have been like 5 or something. Again, that's not a high dimensionality problem where you would be motivated to look for a faster technique. So I increased the number of features to 200. And what we're doing here is we're just generating a random data sets, right? Just random Gaussian random variables for our data sets. So when I did this and reran it, you do find a significant advantage for randomized Pca, a significant speed advantage in training. And then in the next example, he fixed the data set to be at 2,000 instances, and then he's looking at the time complexity as a function of the number of features going from 1,000, 2,000, 3,000, and so on. So I left that, the same, except his number of components was 5, and I made it 10 just to make it a little more challenging, and it didn't take that much longer. So, and again, we find a very significant advantage for randomized Pca in the training time. So I think this is the point that that he meant to make with these plots, but maybe he just didn't have time to fix it. So, yeah. Okay. Any questions on that? Okay. Randomized Pca, we don't have time to get into it, but it's a technique that somehow gets you a speed up. It's faster than ordinary Pca, and I think that Rachel talks about it in her numerical computing. In her, I think she has a course in numerical methods or something like that. I forget what that course is on FastAI that she has. Computational, gosh, does anybody remember the name of that course? I know Srinivas had mentioned it before.
Linear algebra course?
The linear algebra.
Yeah, it's basically Rachel's linear algebra course, but it's really more detailed than that. It looks into fancy computing techniques and so on. Yeah. But anyway, she talks about randomized Pca in there. Okay, so now kernel Pca. So we've seen the kernel trick before, and let's see. I thought I had this. There's a very brief description of it on Wikipedia, which is probably a good idea to just look at real quick. Oh, I meant kernel trick. Kernel trick. Kernel method, call it kernel method. So, you know, the basic idea is that the kernel method, the kernel trick allows you to project your data. It effectively projects your data into an infinite dimensional space, but you don't have to do all those calculations to actually map each point into the infinite dimensional space, because it turns out you can sort of implicitly do it by calculating a dot product with a kernel that you use. And there's various kinds of kernels, polynomial kernel, we've seen this, polynomial kernel, sigmoid kernel, radial basis function kernel is a very popular one that most people use, that many people use. And so the kernel method basically says you can take a nonlinear problem and make it into a linear problem. And so he does that with the Swiss roll data set. Back to, let's see, yeah. So here's the result, you know, using different kind of kernels. You take the Swiss roll data set, which we saw was a 3-dimensional data set, and he's mapping it down, he's projecting it down into 2 dimensions with a linear kernel, with an RBF kernel, and a sigmoid kernel. It's interesting that the sigmoid kernel and the linear kernel sort of move in opposite directions. One of them is, the linear kernel is somehow counterclockwise unrolling, and the sigmoid kernel is a clockwise unrolling. Don't ask me why that is. But yeah, the main thing is that you can see that you can project this complicated data set down onto a 2-dimensional mapping, and that it simplifies things. So that's the idea. You can, since we never get to actually map the data into this infinite dimensional feature space, we can't really sort of use the way that we did before to map it to its 3-dimensional reconstruction, and then see what the reconstruction error is. So there's a special technique that allows you to do that, to get the pre-image, what they call a pre-image. It's not the same thing as a 3-dimensional reconstruction, but this is the pre-image plot. He gives a way to the way to calculate the pre-image plot is RBF is the dot inverse transform method, and this is what it looks like. So this is, let me see, this is Pca, which is the last, which is the Pca that we're, oh, this is Pca inverse transform, whereas we did kernel Pca up here, kernel Pca. So you can get this 2-dimensional projection. I think we already saw that up here. It looks similar. Yeah, that's the 2-dimensional projection. And then to choose the hyperparameters, he's built this little grid search thing where you're just basically looking at different values of the gamma different values of the kernel, and so on, and you just run through that and find the best one from the parameters that you gave it. And this little routine here finds the best parameters and reports them. Let's see, mute. By the way, it's a good idea if people would set their zoom parameters to mute them upon entry to a call, because a lot of people, not a lot of people, but some people forget to do that, and then we can hear you, and it kind of disruptive. So I have to go back and I have to go in and manually mute. It would be great if I didn't have to do that. Okay, so the last technique he discusses is this technique called local linear embedding. There's a bit of a mathematical background to it. It's in the book, and let's see. He shows the equations. Basically, you're looking at linear combinations of weighted weighted linear combinations of the data, and you're trying to find linear combinations that let's see. I think what you're trying to do is you're trying to map this three-dimensional or many-dimensional structure to a local tangent hyperplane. And the idea is that you're preserving local relationships, that is, distances between clusters of points and so on. And there are two basic equations. One is where you're adjusting the weights, and the other one is where you're fixing the weights and adjusting the parameters in the two-dimensional projection space. So you're adjusting the z components in this one. So the first one is a constrained minimization problem, because you want the weights to be zeros if they're not one of the k. Let's see. What does he mean by Cn? Back up to here. I don't know what he means by Cn. He probably introduced
I think that would be closest neighbors.
Closest neighbors, right. So that's a parameter that you specify. You specify how many nearest neighbors you want to include in your mapping. So, and then the weights of the data points that are outside that set of nearest neighbors are set to be 0, and then the weights are set so that they sum to 1. So this is a constrained minimization problem. But the second problem, finding the coordinates, is an unconstrained minimization problem. So you find the z coordinates that that minimize this expression. And then let's see. So this is what it looks like after you do the local linear embedding. And the nice thing about it is that it does what it advertises to do. It preserves you can imagine that the whole thing was the Swiss roll, but it's basically unrolled the Swiss roll, and there's some distortion, right? It's not, there's some stretching on the left-hand end and there's some squishing on the right-hand end, but it has maintained the, similar points, clusters of similar points to be still close enough to each other, right? The points with the values of that t parameter, which are encoded in the color, are all preserved. They're near each other. The yellow is all the yellow points are near the yellow points, and the red points are near the red points, and the black points are near the black points, etc. So that's local linear embedding. He also talks about several other techniques. I'll go back to so he talks about multidimensional scaling, which reduces, I'm just quoting from the book here, reduces dimensionality while trying to preserve the distances between the instances, which is a good thing to do. Then he talks about this isomap technique where you're trying to map the data set into a graph, into a nearest neighbor graph. And the goal of the isomap technique is to preserve the geodesic distance in the nearest neighbor graph, and that's defined as The geodesic distance between two nodes in a graph is the number of nodes on the shortest path between those two nodes. So that's a different kind of optimization, but it's also trying to reduce the dimensionality while preserving important information. There's the TSNE, which we've seen. It's mostly a visualization technique, and its goal is to reduce the dimensionality while trying to keep similar instances close by and dissimilar instances far apart, which seems like a reasonable thing. It's mostly used for visualization, as I mentioned, and then the last one he talks about is linear discriminant analysis, which reduces dimensionality while keeping the different classes as far apart as possible. And this is said to be a good technique to apply before reduce dimensionality, to apply before another classification technique. So he mentions here the support vector machine. So you could run linear discriminant analysis on your data before running it through support vector machines, and that way you could cut down the dimensionality by quite a bit, and therefore you'd save a lot of compute time on your support vector machines classifier. It gives a little comparison of these three techniques. Here's the TSNE. It keeps dissimilar instances far apart, right? And ISOMAP seems to like unroll the Swiss roll, kind of like LLE did, except with maybe a little bit less distortion. And MDS seems similar to multidimensional scaling, seems similar to one we've seen before. Which one is it? Is it the clockwise one or the counterclockwise one? One of those two. So that's a counterclockwise one. So it's similar to this one, the linear kernel in the Kernel Pca. So I think I'm going to quit there. Are there any questions about the rest of Chapter 8? All right, well, I'm going to turn it over to Steve now. Let's see, stop my sharing. And over to you, Steve.
All right, everybody. Happy Wednesday evening. I guess it's maybe Thursday morning for some of you. And we're going to go through unsupervised learning and start that tonight. I'm going to give you guys about, I'm going to give you guys about 15 minutes for, let me see, I want to share my screen. Okay, there we go. I want to give you guys about 15 minutes to read through the material, but before we do that, I will just quickly hit on a few highlights. So just because I always do this, my financial disclosures, I have no conflicts of interest. I'm not receiving any payment from TWIML for this. If I was, I think Joe would probably ask for his money back, and I do hold stock in Alphabet. So, you know, thinking of the spectrum of what we're doing, we're going to go into unsupervised learning and clustering tonight. And, you know, supervised learning is what we've been doing with labeled data, and that's most of the classifiers and also segmentation algorithms that we haven't covered yet. There's unsupervised learning, which deals with unlabeled data, and a lot of people like to use this unlabeled data because it's a lot easier to work with, and it's a lot easier to obtain for them, because let's face fact, labeled data is expensive. And this is the clustering algorithms that we're going to be talking about tonight, as well as GANs. Sitting in between the two of them is semi-supervised learning, where basically you say, I have some labeled data, but I'm lazy and I don't want to label more, so I'm going to use this unlabeled data that I have and trying to make a coherent data set out of all of it. One thing that I would like to address before we start, because I think it's a potential point of confusion, depending upon where you are in the learning spectrum. K-nearest neighbors versus K-means. We're going to be discussing K-means tonight. K-means is a clustering algorithm, which is similar to classification, but it's more like an assignment. It's better for exploratory data analysis, in my opinion. And basically what you do is you take centroids and you maximize Euclidean distance. We'll read about that, and then we will go into that in more detail. This is compared to the K-nearest neighbors algorithm, which is a fundamental and very basic classification and prediction algorithm, which is based upon applying a distance metric, usually the Euclidean or L2 distance, to the K, whatever number you choose, 4, 5, 6, 10, whatever, neighbors, to classify a new data point. It's not typically a great predictor. It's called considered a weak predictor, but it's pretty easy to implement, and it's kind of trotted out occasionally as a basic example of an easy to program classifier. So we're going to read pages 235 to 244. I'm going to give 15 minutes for that, and I hope that's okay because there's a lot of code and a lot of the things are repeated, and there's a lot of notes and discussion in actually the notebook that's not necessarily in the book. I have given you a link to a collab in the channel. It's my collab that I've based off of the ML2 collab. It's slightly altered. And we're going to talk tonight about the classification versus clustering, K-means algorithm, hard and soft clustering, and the inertia measurement. So,
Hey, Stephen, may I make a comment before we go to the reading?
Sure.
Yeah, I think you've hit on a really great cautionary point here, just to help people along, because it confused me too when I first saw that K-means and K-nearest neighbors. K-means is what we're going to talk about tonight, and you know something about K-nearest neighbors, but the most important difference between them is that K-means is an unsupervised learning technique, but K-nearest neighbors is a supervised learning technique. You already know the classifications of some of your data, and you're finding the nearest neighbors to the data of known class. So that's the fundamental difference between those two techniques. One is unsupervised and one is supervised.
Yeah, that's a great point. I should have brought that up, but that's a completely true and great point. But you can actually use both of them for classification. Just one is supervised, one is unsupervised. Okay, so I'm going to put us down for 15 minutes here. Let's see. Okie doke. So I'm just going to warn you guys that I have my kids with me tonight, and they are, like most children, unruly and ill-behaved because I'm a terrible parent. So if you hear them in the background, I apologize profusely. So let's just quickly, I am hoping that I am showing you the screen with the Geron chapter 9. For some reason, I'm not doing that. You need to let me know. So I'm just going to quickly go and start in with clustering. Basically, when I think of clustering, I think of it as an exploratory data analysis. You get a bunch of data, and the question is what are you going to do with that? And how are you going to kind of attack it? Is it one thing? Is it more than one thing? Is the data, smoothly distributed? Is it heteroscedastic? Is it bimodal? What's the distribution? As you go through data that may be unfamiliar and evaluate it, one of the things you can do is you can use a k-means type algorithm to cluster that data and look at the clusters of data and see how many different entities you're dealing with, if you can easily separate them or not. So, they talk about it being used for dimensionality reduction, for anomaly detection, semi-supervised learning. All this stuff is great. Let's get into the meat of k-means, okay? And I'm going to jump now to the Colab. And make sure I am sharing this. Okay, cool. So I'm going to run this along with you guys. Some of the things take a little bit longer to run. We're going to start first with our initialization, and we're going to go into classification versus clustering. And I'm going to be blunt with you about this. There's something in this that doesn't work correctly, and I spent about an hour trying to get it to work, and I think it's just it's something stupid, and I'm not going to waste a lot of time on it. So I'm going to alert you to it. I think it's just because of the way that Google has done something or the way that NumPy is doing something, and it's not very important to what we're doing today, but I'm just going to let you know. I hope we don't get bogged down on that. So we're going to load the Iris data set from scikit-learn, and this is like one of those fundamental basic data sets that everybody kind of plays around with and starts with. We'll load the data from it. We have the 3 different classes of plants: Setosa, versicolor, and virginica. The type of Y is actually an integer. I'll come back to that later. And so we're going to plot this out, okay? And we can see here on the left that we have 2 well-defined clusters. You have this cluster down here, and then there's kind of range here. And this cluster down here is the Setosa variant, which has the smallest leaves, and there's a spectrum for the versicolor and the virginica, where the versicolor is a medium-sized leaf and the virginica is the larger leaf, and those kind of grow progressively, but there is no really good delineating line between the two. So when we plot them without their colors and without their labels, you see that there are 2 different areas, but you can't really delineate between the blue versicolor and the triangular virginica. So this is where things kind of go down the tubes a little bit on this Gaussian mixture, and I'll show you how. So he said, okay, well, we can separate these, by using a mean curve shaped distribution. So we do this, and so we see that there are 3 clusters. There's 1, 2, and 3. And just so you know, this number is supposed to be like 145. It's not. It's 0 on my collab when I run it. It's completely unimportant. I think it's related to a data type error, or not a data type error necessarily, but an unintended port of the data, and the data is different for some reason in collab than it is in the implementation that Geron was using, and for that reason I played around with it for a good hour, couldn't get it to work, and I'm not going to waste my time on it anymore. So just for kicks, if we start changing things around with this Gaussian mixture, and if you go into scikit-learn, you'll start seeing that there are more parameters than just what's stated here. He labels the number of components, that's the number of clusters that you are expecting, and it gives you a random state, and we're chaining the fit and predict with it as we can in scikit-learn. So if you actually look at the scikit-learn documents, you can actually add different tags. There's the verbose tag, which gives you a look into what the process is doing, and warm start versus cold start. We've already trained it somewhat here, so we can use that data instead of just starting over from nothing, new random initialization by using the warm start true. So I just threw that in for fun. And we redo this, and then we can plot. And here we come out to 2 clusters. I just commented this out because it doesn't do anything if you run it. Actually, it does. I'm sorry. But if I set it to 2, and let me comment this out. Oops, it's going to break. So now we got 2 clusters. So the number of clusters that you choose when you are choosing, in your clustering algorithm is going to, define your worldview and what you get out. So this is a circumstance which I think it's good to start playing with things and to try different, combinations and optimizations. As we go along, we will see that there are ways to automatically optimize for k-means, and we'll discuss that actually next session. So let's get into the k-means algorithm. And k-means is really just, the k serves as a alternative to n, so some sort of integer number, and means is the mean distance. So we're going to make some blob-like clusters. These are the centers on a Cartesian coordinate. We're going to make 5 and put them into a NumPy array. So we print out the length as a check, and we see we have 5 different centers. We're going to make 2,000 samples with the centers of the blob centers and give them a random state. Now we'll plot them. And so we come out, and you can see that there are 5 different clusters, 2 larger, well-defined, 2 larger and kind of amorphous, less defined clusters, and 3 smaller, tightly defined clusters. Everybody with me so far? Any issues? I'm checking the chat. I don't see anything, so I'm moving on. So we're going to train a k-means cluster on this data set and try to find the center of the blobs and assign each of these data points to the closest blob. So we import k-means, This is the scikit-learn documentation on k-means. And basically, we have to give the number of clusters. Let me just make sure I'm sharing this. Yeah. And there are different ways of initiation, and we'll get into that in a little bit, okay? The number of times that you run it, just the same way, with a random forest or a bootstrap or a bag, you give it a certain number of times to run. There's the trade-off of increased computational complexity with a higher number but improved accuracy, maximum number of iterations, the tolerance, which is set at a default of 0.0001, I believe, and these pre-compute things, which are deprecated. The verbose tag, which I discussed with you before, random state, and that's pretty much about it. The algorithm is also relevant, and we'll discuss that later. So we're going to set the k to 5, and we're going to allow the k-means object to be k-means with number of clusters equal to what we set it at 5. Start with our random state of 42 for reproducibility. We put in the algorithm, which is the auto algorithm, and we're going to make it verbose, so that's going to give a little bit more information when we run the algorithm. Y predicted, or Y hat, is going to be the fit predict of k-means on the object X, and then we're going to check to see what the k-means labels are. So we run it, and apparently it has some inner loops, and it's giving us a number called inertia, and you'll see this number of inertia is bouncing around a bit, but starting to try to center maybe on something about 236 here, and it gives us an array of different ordinal numbers, and those integers look like they are almost classes, and it's actually the assignment of the cluster that these ordinal numbers represent. Are we all good on this so far? All right. So just to confirm that we had 2,000 different predictions, because we have 2,000 data points, and each of these data points belongs to a different cluster, as evidenced by this, and is 0 to 4 instead of 1 to 5. We can check the labels by the labels object, and we can see it's basically the same thing as this array for ypred. And we'll test it to see its equivalent, and it comes out to be true. If we pass the cluster centers operator, we'll get back these 5 pairs of Cartesian coordinates, which are going to be the center of the clusters that the k-means algorithm calculated. He notes that the k-means instance is label preserving. And what he means by that, the label is the index of the cluster that instance gets assigned to. So whatever, if it was cluster 1, cluster 2, cluster 3, cluster 4, or cluster 0. And once again, these labels are just the clusters. So if we pass new data points to the algorithm, we can predict new instances. So we pass it a 0, 2, a 3, 2, a negative 3, 3, and a negative 3, 2.5. And then we'll use k-means predict on the array to see what we get. And so we see that these first 2 data pairs are going to correspond to cluster 0, and the last 2 are going to correspond to cluster 3. All right. Any questions?
So what exactly are we checking in cell number 25? We're just checking whether the labels exist, or rather the predictions exist in the labels. That's all the check is?
No, we're checking to see if the array that's output by ypred are the labels. It's the same thing.
Okay.
Okay, it's just you can access it whichever way you choose, but the object way to do it, the more Pythonic way to do it, would be k-means.labels.
And in this case, yeah, the point that he made in the book, like, still kind of confused with the context of label versus an index per se.
Yeah, I'm a little confused to that. I think that the idea being is that because you're doing unsupervised learning,
Right.
the assignment of a label is somewhat arbitrary because you don't have any definite ground truth.
Correct.
Says, okay, this is cluster 1, this is cluster 2. If we were to pump up the k to maybe like 20, all right, it would start drawing, it would start taking different clusters at arbitrary order. So the index, I mean, you're indexing these, these different clusters by virtue of, the number of, the k number that you've chosen. And as k varies, the value or the index of the class it's assigned to will change. That's at least how I interpret it. Maybe someone has a better way of thinking about it, but that's how I think about it. Because when you think about it, if you look back to this image, right, all these dots are kind of just the same kind of blue. You can't really tell between them, a priori, yes, this looks like a cluster to me. This looks like a cluster to me. This just looks like a cluster to me. And these two look like a cluster to me. But, there's nothing that is a labeled data point with each of these values to say, okay, well, this is something absolutely different than this.
Right. Okay.
Yeah, I think you're absolutely right, Stephen. I was confused by that statement too. That on page 239 in the book, this is not to be confused with the class labels. And the statement tends to make more confusion than it undoes. But I think your point is that classes are for supervised learning problems, and here clusters are different because we're sort of ad hoc, we're empirically determining the clusters. There's no supervised, nobody's telling us the answers. And I think that's the meaning of what he's saying. It's just a very subtle point.
Okie doke. In that case, I'm going to keep going on. And let's talk about the decision boundaries. So he gives us this great plot subroutine. And now we're going to plot the decision boundaries for these 5 different classes. And this is how the k-means is kind of carving up the territory. This is apparently called a Voronoi plot. Okay, didn't know that. So if you're using clustering, I guess that's a standard thing to do. He makes a comment that some of the instances near the edges were probably assigned to a wrong cluster. So this is probably more related to this than it is to here. But that's the nature of the beast. Ditto with these guys. These are probably not yellows, but they're probably purples. But you don't expect it to, be a perfect classification with an algorithm like this. So let's go on a little bit and let's go into hard clustering versus soft clustering. And it involves matrix math that I don't understand sufficiently. So I'm not going to, pretend to. what he's doing here is he's basically saying, look, the k-means transform object, okay? And he's transforming x new, and x new is this, these four values that we gave the algorithm here. So we're going to transform these new ones and see what the distance is to all 5 of the centroids. So you're going to get 5 values out of that, and those 5 values represent that data point, okay? So it's not assigning it to a cluster. It's not, you know, doing a form of indexing or classification. It's giving it more of a positional reference in space, but the reference, instead of a Cartesian reference, as the 2 values that we had before, because remember we had 4 pairs of two values. It's relative to each of the 5 K clusters and the distance to that. So that's this, and then he does some matrix math on it to show you that this whole mess is the same thing, and the numbers are identical. So that's fantastic, and I can't really comment further on that, so I would just use the transform to put it into this setting. Now, he's going into k-means. You know, obviously it's a simple form of unsupervised learning. The way it works is you initialize the centroids randomly, and then you place those centroids, you know, at those locations, and you kind of see if it's good or not, and shift them around and move it, and you keep updating until you have, you know, a stable iteration. So it's an optimization process. And one of the things that is a little bit confusing, but he goes into it in a bit, is that the k-means process that we're using in scikit-learn isn't the original k-means. It's actually something a little bit more advanced. So the original k-means algorithm, you set init to random and init to 1, and algorithm is equal to full. And the algorithm full doesn't mean what you think, and we'll get into that in a bit. So he runs it for 1, 2, and 3 iterations to see how the centroids move around. And here's the plot, which is kind of cool. This is fun. So here's where we start, okay? So these are the randomly chosen areas and the Voronoi diagram. So initially, you have, you know, things that are not equivalent to what we saw before. And in fact, this doesn't even exist anywhere near where we would think the centroid center is. It's off to the side. This is over here. This is pretty good. This is pretty good. This is definitely off to the side. And as we go on, you can see that this centroid keeps moving closer to the center of what we would expect this centroid to be. This also moves closer to the center. This is doing better. This is doing better. This is still somewhat off, but it's marginally improved from here. So the stuff kind of moves, and obviously the more iterations you give it and the better selection you give it, the better it'll work. Any questions on that?
Yeah, why are the 6 figures there? 3 iterations, 1 original init.
I think that so when we're plotting, the first plot is just the original.
Original, yeah.
Okay. I mean, this is just, he's not even plotting, you know, anything yet, but these are the variables that are, you know, randomly chosen. Okay. Then we're going to apply that data, because subplot 321 right here, okay, it's the centroids. Plot number 322, we add the decision boundaries. Okay, so nothing is, there's nothing really happening. This one, okay, we're plotting it again. This is iteration 1. Okay, so this is iteration 1, this is iteration 1, this is iteration 2 and iteration 2, and the last one is iteration 3. So I think that possibly this could be kind of duplicated. To me, this looks like it moved. Maybe what he's doing is he's showing that the decision boundary hasn't moved yet, but the centrum has moved.
I see.
Exactly. The centroids are moving.
Yeah, plot centroids, because here, he's plotting the centroids of iter 2 with the means boundaries of iter 1.
Okay.
Yeah, because in each case, isn't it a two-step process? You allocate the points to the nearest centroid, and then you recalculate the centroids, and then you reallocate the points to the nearest centroid. So it's always a two-step process.
I see. Okay.
To converge, right? First, you select random centroids, then you allocate the points to the nearest centroid. After you do that, you recalculate the centroids with the points you have allocated to the nearest centroids. So every step is 2 steps.
No disagreement? Okay. Are we clear on that?
Yeah, just kind of that the boundary doesn't look like it's moving, but yeah, we can look into that later. The boundary looks constant throughout to me.
No. Look at this boundary. That's definitely moved from there.
Yeah, you're right. Yeah. Okay.
Yeah. For me, it's on a wider screen on a separate, and the orange is different. That orange section, it's different on all of them.
On all of them?
Mm-hmm.
Oh, okay.
Yeah, I agree. Okay. Cool. I mean, if you look at this point on the triangle is touching
right,
the bottom, okay? It's still touching the bottom. Now it's moved up a little bit off of the bottom, and then it moves up a lot off of the bottom. So you have 2 sides on this orange. Now you have 3 sides here.
You can widen the image and see for yourself.
Yeah, then I'm kind of confused that why do we have 6 diagrams again versus
He wants to tell the story.
I think that's because he's running it for 1 iteration, 2 iterations, and 3 iterations. 1 + 2 + 3 is 6. And I think that's what you're getting.
It's hard to see this, but the label on the graph says update the centroids initially randomly, and then second label the instances. So this is the part that we're going to draw the decision boundaries, and this is the part that we carry over whatever the decision boundaries are. And that makes sense, because if you look at it, this decision boundary and this decision boundary are the same, and this decision boundary and this decision boundary are the same.
Okay, that makes more sense. Okay. So you're carrying over and then you're continuing from there, I guess. Okay.
Yep. Okie doke.
The thing that stands out, though, is that it's doing a really bad job on the centroid of the lower left, the second one from the bottom. There's a cluster of points, and it's not getting the centroid anywhere near right.
Yeah, I mean, I think that if we ran this for another 10 to 50 steps, it would be fine. Remember, we're just running it for 3 steps. I mean,
yeah, I'm doing that as we speak.
Yeah. Okay. Yeah. All right. If you're coding it, I'm not gonna code it, but just give us a heads up when you get to it.
No, it
Okay.
takes a long time, so
Okay.
yeah, might as well just move on.
So talking about k-means variability, let me go back to the, sorry. So I want to go back here, okay? And, you know, he makes some points here that I thought were helpful, you know, discussing how these decision boundaries works. You know, first of all, you know, the algorithm is not great when the blobs have different diameters because it's looking at the distance to the centroid to assign, you know, a particular instance to a cluster. So, you know, the difference between hard clustering and soft clustering is not just that position, but it's the idea between assigning a particular ordinal data class versus, you know, giving a true measurement. And, you know, there's some people that, you know, speak a great deal about this and feel that you lose information when you kind of assign a class or an ordinal data point to something, and you should use a continuous, you know, range of data points instead. Frank Harrell out at University of, he's out at Vanderbilt, chair of their statistics program, speaks a lot about that. And I think what he's saying from an informational theory perspective is correct. So using the soft clustering allows you to preserve some information that may be helpful to you in the future. So one of the things that he mentions is that if you have a high dimensional data set and you transform it this way, you can actually, you know, have dimensionality reduction from whatever your high dimensional data set is down to a lower dimensional K data set. I'm not sure what I would use this for in terms of, you know, my area of image processing, but I'm pretty sure that there are other areas that this technique might be useful, and I just can't think of any. So if anybody has a good use case, feel free to suggest it because I can't think of one. So we've talked about how you make your initial guess, you update that, you center them, and check and see if it's moving or not. You know, try to a smaller guess, try a better guess, and keep, you know, seeing how it goes. So the speed of this kind of approach is quick, and k-means is felt to be, you know, a fast clustering algorithm. We went through this. And he talks a little bit about here the issue, you know, do you converge to a global optimum or a local optimum? Depends upon the initialization, you know, and raises the possibility of a lucky initialization. If you're not familiar with that term, it's that, you know, when you are doing any sort of optimization problem, you know, your initial random state tends to reflect upon your outcome. If you get a lucky initialization, good numbers for your data set, things might work well. If you get an unlucky one, you may not converge and you may just abandon it, but it's, you know, and when it's more of a function of your initialization rather than an actual problem. And this is, you know, this happens more than can be dismissed, you know, promptly in deep learning, but that will be discussed in a few weeks. Okay, so what you can do is you can improve the initialization of the centroids to avoid as much of an influence in lucky initializations. Let's see, where is my, I hope I didn't blow that out. Did I don't need that. I think I unfortunately closed out my.
Are you looking for your notebook, your Colab notebook?
Yeah, I think I closed out my Colab.
No, you didn't. You have it with your slides. Go to the same one where you had your slides. It was the tab over, or did you just close that?
This is not mine. This is his. Okay, unfortunately, I am going to have to rerun just a little of this. Maybe, maybe not. Let's see. All right, so let's see what we got here. What number is that? No, not necessarily. Okay, cool. So did this. We did this. We did this. Okay, and we just did this. And now we're getting back to this K-means variability. Okay, cool. Thanks. All right, so by improving the approach by running it multiple times or with multiple different seeds, you can have different solutions. Now, when I ran this, I got to be honest with you, I wasn't particularly impressed with the convergence. I mean, to me, these looks like very similar. Okay. Just make sure you guys are seeing what I'm seeing.
Yeah, we're on your Colab notebook.
Okay, so you're seeing this right now. So for kicks, let's change the random state on this a lot. Let's see if it does anything.
How many iterations are these running for? So
I'm sorry?
How many iterations are these running for?
The default is, I think, 10 and 300,
Oh,
if I
okay.
recall correctly, But if I change, I changed the random state now, and we get a very different appearance. All right. So that's a real big difference. So the first one, it was a trivial 19, I think was trivial. I couldn't really make a difference. I was looking at that and thinking to myself, okay, the colors changed, but nothing else changed. Versus that. Okay. So previously when I showed you this and we ran it out, it was mentioning this number, inertia. And inertia is going to mean it's a measure of the distance between each instance and its centroid. So how far away is the distance between the point and the center of the centroid that it belongs to, right? So you calculate that with the inertia object, all right? And that in this case is 211. And what it is the Euclidean distance, which is the squared distances. So if you take this, you transform x, and you sum the length of x here and the labels. So for each one, what's the squared, you'll get the same inertia figure. So he makes a comment about the score method returning the negative inertia. Why negative? Well, it's because a predictor's score must always respect the great is better rule. And that to me does not make sense. So if anybody knows the context of why he's saying that, I have no clue. Sorry, guys. Do not know. Anybody have?
I think it's more a convention, Stephen, of in sklearn, I think they want, or the convention of score of anything being more positive is better, and he wants to stick to that convention. So he flips the sign. That's the way I understood it. That in sklearn, the score, in general, if you take the score of anything, then you want larger numbers, more positive numbers to be indicative of better.
Right. So that to me is indicative because it's a negative number. It's indicative of this is not a great solution. That's what that would indicate to me. Does anybody have an opinion on that? I mean, it's kind of an arbitrary, it's an arbitrary number.
Yeah, here it's much more relative, meaning like minus 211 would be a better score than minus 237.
Right.
That's all he's trying to say, I would think.
Okay.
But it's a good question as to whether the fact that it's negative indicates, and whether you would, but I think since distances are always positive, it will eventually end up that all inertia numbers, when treated as scores, will probably be negative.
Yeah, that would make sense. So just to, recapitulate, and if you go back to page 243, I think it's relevant to note that the definition of the model's inertia, okay, is the mean squared distance, or the L2 distance, between each instance and its closest centroid. So in my mind, if these are the centers of the centroids, and we were to pick this random point right here, okay, the closest centroid is going to be this one, and we would then be measuring this Euclidean distance between this point and the center of the centroid as a 0, 0, essentially, to get that distance. All right. Moving on.
The score actually is, it depends on how the data is arranged, right? I mean, if you have tight clusters, then if the clusters are tight, like those circular, like the circular ones, the small tight circular ones, then the scores are going to be low because everything is so close. But then you have these spread out clusters so those scores are going to have to be high. So a high score doesn't necessarily mean that the model is bad. It just means that your data is spread out.
Yeah, good point. Okay. All right, multiple initializations. So the solution that he suggests is to run k-means multiply with different random inits and select the solution that minimizes the L2 distance. For example, here are the inertias of two bad models. So init 1 and init 2, okay, they're slightly different. This one's 211, this one's 219. I think the first time I ran this, I actually got very similar ones for each. So 219, if we flip the score, it would be negative 219, which is lower than 211. So this is the worse, in quotation marks, of the two models. So when you set the n init hyperparameter, scikit-learn runs the original algorithm that many times and selects the solution that minimizes minimizes the inertia. By default, it sets n init equal to 10. So if we're going to run it with 10 random inits, we take k-means, 5 clusters, we set init to random, we give the number of inits, we're using the full algorithm still, random state is going to be 11. So let's run this, then afterwards we're going to fit it and see what happens. So printing it out, or showing it, this is very similar to what we got the first time, which means that the optimum k-means solution is 5. So for fun, let's take k-init and make it 50 and keep the same random state. Looks the same. Let's drop n init to 2. Actually, let's make it 5. And keep the same random state. And it still looks pretty much the same. Maybe this is moving a little bit. I can't quite tell. So then we're going to go on to k-means plus plus. And the thing is that we've actually been doing pretty much is we've been using k-means plus plus because that's the default it's the default algorithm of scikit-learn. And the way it works is you take one centroid chosen at random from the data set, take a new center and a new instance with this probability term here, which is the distance squared of that instance divided by the sum of all of the distances, I believe. And see that, and what that does is that the instances that are further away from the chosen centroids are more likely to be selected as centroids. And you kind of keep repeating it. And this algorithmic improvement means that it is less likely to converge to a suboptimal solution, so you can decrease n init to a lower number and reduce your computational burden. I mean, not as critical for us these days unless you're doing really large data sets, but once upon a time, this I think was pretty important. So to set the initialization to k-means, simply set init equal to k-means plus plus, and that's actually the default. So you can see here, if we just run it by itself, init equals k-means plus plus. 300 iterations, basic, n init is a 10, and I think they give you like 8 clusters. This, okay. And we'll do a good init here, and these 5 initializations, Cartesian coordinates, 5 clusters. This data, we're going to take the n init equals 1 as opposed to what we were doing up here, 5 and 10. So we can drop the number of random initializations down, and then the random state is what's applied. And we get a similar inertia to the optimal solution that we've gotten before. I probably don't have the math knowledge to explain this any better. So if anybody wants to jump in and correct anything I said, if I didn't say it correctly, feel free. But I think that from a practical standpoint, the important thing to do is that the important thing to know is that your k-means algorithm is, actually using this more advanced algorithm. So it kind of is underneath the hood from your perspective. It probably doesn't impact you that much.
So Steve, I'm just looking at that algorithm, and it's kind of, I don't understand the exact reason why they have squares, the sum of the squares and all that, but I mean, it is plausible that what they're doing is pushing you to choose examples that are farther, choosing the new centroid that's far away from the old centroid, because if the distance is too close, then, well, it's choosing from a probability distribution, and points that are close to the previous centroid have a low probability of getting chosen, whereas points that are far away from it have a higher probability of getting chosen. So I think it's just that intuitive notion is probably enough for us to just sort of take away from this.
Yeah, I don't remember if the original k-means algorithm used the Manhattan distance rather than the Euclidean one, but I thought that it used the Euclidean distance.
Oh, refresh my memory on the Manhattan distance.
Manhattan
Is that
distance
just, it's just the sum of the components?
It's just, like L2, it's the absolute value of L, it's the absolute value of, x2 minus
delta
x1.
X plus, yeah, delta X plus delta Y,
and then,
yeah.
And then, L2 is the square.
Okay, got it.
So.
Yeah, Manhattan, I guess now I'm remembering Manhattan is like, they're talking about streets that are laid out, north and south in a grid. And, this is the distance that the taxi cab driver is more interested in is, the sum of the distance to the east plus the distance to the north that he has to go, rather than he doesn't care about the Pythagorean theorem.
Right, because he can't drive he can't drive across the triangle.
Yeah.
Okay. Accelerated k-means, this is a trick that they're using to basically compute it faster. So the main point of this is that the algorithm that you're using, we've been using algorithm equals auto in our, see, algorithm equals full, okay? You can use a few different things. I think, if I recall, you can use auto, full, or LCAN. And let me see if I can, yeah, here we go. Oops. It's hiding behind here. Yeah, so algorithm is just auto, full, or LCAN. The default is auto, okay? The LCAN algorithm is, I believe, a faster algorithm that you can use. The only problem is it uses the triangle inequality that you just brought up. So instead of going left or going west a block or two and then up 5 blocks, you can actually cut through and use a shorter distance by a triangle. But that only works if the data is well-defined, like well-populated or almost even Gaussian. If it's sparse data, it doesn't work as well, and I believe that the original algorithm works better. So the auto switch allows scikit-learn to just decide on its own which one works better. So basically, so they say, full is the classical algorithm, and auto chooses LCAN. So, okay. Let's go back to the Colab. So they talk about, and he'll show you that if you use the LCON algorithm, it takes you 87.6 milliseconds per loop. If you use the standard EM algorithm, it's going to take us 126 per loop. So, okay. Perhaps it's important to you, but I'm not sure. Tuck it away. I'm not sure really if it is that helpful or useful. Now, if you're dealing with really large data sets, using a mini batch actually might be useful. So there's mini batch k-means. Cluster is random state. You fit it, basically it's just the same, okay? The batch size, the default batch size is 100. If we use this to calculate on our 2000 sample data set, we're getting a similar value of inertia of 211. Now, I could imagine if you're doing really large analysis on really big data, or if you're using some sort of like add technique, on for add spies or cells or anomaly detection, something that that you're using like really large amounts of data, you may not be able to fit it all on memory. So the mini batch technique might be useful here. So they give an example with MNIST. This is going to take a second. And you do your test train split, and you write it to a mem map. And then you use the mini batch k-means on the mem map. They drop the batch size to 10, and you fit this data set. Now he talks about if your data is so large that you cannot use memmap, things may be more complicated. You write a loader function, train the model by feeding it one batch at a time. So now the batch size is 100, and its size is 500. And we're getting, actually, I think a little bit better of a score. Yeah, 211.93, and this is 211.70. So it's a little bit better with that more comprehensive and more extensive iteration. And just like everything, the more you decrease your mini batch size, the more hinky things will get, and the more number of iterations, the better it'll get. So just kind of tuck that away. Said to be faster than regular k-means.
What was the init size parameter again, sorry?
I'm so sorry?
What is the init size?
500.
Controlling? Yeah, what is that controlling again?
The init size, I believe, is controlling the number. Init size. Let me check in mini batch k-means. That's a good question. So the init size is the number of samples randomly sampled for speeding up the initialization. So I believe instead of sampling all 2,000 samples, each time you run, you're going to mini batch based upon 500.
I see. So your batch size is what you're grabbing in your case, just 100 samples out of these 2,000 samples.
No, my 100 samples are going to be out of 500 samples out of the 2,000.
Okay. This says number of samples to randomly sample for speeding up initialization, right? So isn't this like where your init is grabbed from, like those points? Your randomly initialized points? Or yeah, never mind. Forget that.
The only algorithm is initialized by running a batch k-means on a random subset of the data. So I believe that that random subset is what the 500 data points represent.
Okay.
And then when you're running a mini batch, you're going through all that data. So you'll go through the 500 data points, but you're going to go through them. You know, I think the mini batch in this was 100, if I recall.
Mm-hmm.
So you're gonna go through them 100 at a time. So first 100, second 100, third 100, fourth 100, fifth 100. Then I went through the 500, pick another 500, first 100, second 100, third 100, fourth 100, fifth 100. So in that, you know, in that respect, it's a little bit like bootstrapping.
Okay.
Okay.
Yeah.
Okay. Any other questions on that? All right. So the mini batch k-means they're making the point, or he's making the point that it's faster, but performance is often lower, which makes sense because you're sampling from the original distribution, so you're discarding information. So so now we're doing 100 iterations here. And, you know, sometimes when you click these things, you kind of wish you didn't. So I'm just going to show these. Well, maybe we have a few seconds left.
Just a quick note on now. The mapping that was not matching for yourself in the beginning.
Mm-hmm.
I think it's just that it's an unsupervised problem. So you're still categorizing them into 3 groups. It's just that your group numbers are different when you're trying to originally compare it with Iris dataset. So if you change the order around of 210 to 012, then they match. It's just that.
So it's assigning them randomly to a group.
Exactly.
Yeah.
That's why it was not matching.
The initial state is different. It doesn't match. Okay, that's good to know because it was really annoying me. I spent about like an hour on it. I'm like, oh, I hate these things.
Yeah, no, he's put this random seed in a lot of places in the book, but still things don't match up as the version changes.
Well, you know, that's something that's real, and it's a real issue in a lot of, you know, machine learning, and it gets to be a real issue in deep learning because, you know, we have huge problems with reproducibility, and it's not only just, you know, the random seed. There's multiple random seeds that you have to consider in TensorFlow, and
they're pretty much like hyperparameters nowadays.
Exactly, and then you actually have to think about not only that, you have to think about your Linux kernel. You have to think about, you know, how many screens you have open. You know, if you're running it on your home computer, you know, and you're using your graphics card, you know, it's taking up some memory. So it's changing the state, you know, from a virgin GPU, you know, and then even the GPU model is going to change, you know, the training. Less so. I mean, you know, I've noticed that Google Colab seems to do a better job in reproducibility, at least compared to my own machine. But I think that they've kind of figured out the areas that you can go down the tubes. But I still think that if you train it on a K80 versus a P100, you're going to get a different set of numbers for the same Linux version and CUDA CUDNN version and TensorFlow version. So it's an issue. So okay, we're at 56.
Yeah.
And here's the beautiful graph that's going to result when we plot this. So the bottom line is that k-means is nice and smooth. Mini batch k-means is going to be a little bit more irregular. The left graph is inertia. The right graph is training time. And obviously training time increases substantially with the number of Ks. And in mini batch, it's a much lower linear increase. So that's basically most of what I got for you today. And next time we are going to we're going to discuss cluster optimization and pre-processing and I haven't prepared it, so you'll have to wait till next time. So